All right, so now we're going to talk about three different ways of defining probabilities. So our first way that we're just going to hit upon is called the intuitive method. Now, the intuitive method is not something that we focus on in a basic statistics class, and usually not even in any statistics class, but it's important to know that it's out there. So the intuitive method for finding a probability, an example of that would be, what's the probability that another planet like Earth could exist in the universe in the next 4 million years? According to Professor Watson, this is less than 0.0001 chance. So in other words, it's very, very unlikely that it's going to happen. Now, how does Professor Watson assign this probability of 0.0001? Well, Professor Watson is a astrophysicist, I believe was what he was. This came from the internet. It wasn't just made up. So he decided that, based upon his knowledge, and that was his knowledge of, okay, what have we discovered so far? What have we discovered about planets out there, even in our universe, and what are the compositions that it would take to have life, what are the special circumstances, and he took all these things into account and he came up with this probability. Now, there's no hard and fast way, like the next two methods of finding probability, of saying that there's a 0.0001 chance of having a planet be discovered in the next 4 million years that would be like Earth. But he has certainly used his intuition, and that based upon education, of course, to find that probability. So enough said. The next one, the really important one here, is our relative frequency probability. Now, relative frequency probability, in terms of what we do with this in statistics, this is kind of like our sample statistics that we talk about. This forms our sample information. So, relative frequency, this one says if what I observe out of how many possible observations there are, that's going to tell me the probability. So if I have event A and I write probabilities as P of A, like a function, right? So the probability as a function of what's going on in A, we write this probability as F over N, where this F is the frequency of occurrence. So this is how frequently you observe this out of the number of outcomes. So how many times did we look, and then how many times did we see this happen? And that's how we find relative frequency probability. And this comes in when we do experiments or we do observational studies, and we say, okay, well, what happens? So we did this in my classes by actually all together we flip our coins, and then we put relative frequency probabilities together to do a few different things. But one of the things that we can do is that we can flip a coin 15 times and observe the outcomes. So in my coin flipping of 15 times, and I just can do this by flipping a coin or whatever, and you can do it as well. It's not going to come out to the same thing every single time because this is based upon relative frequency. It's a sample. It's not what's actually going to happen in theory. It's just based upon a sample. And we should already know from our chapter 1 studies in a basic statistics class that there's a difference between sample and population. And relative frequency being sample, population is the next thing that we study, which is our theoretical. So I'll leave that for a second here. Anyway, I have observed the number of heads. So H is defined as my event of the number of heads in a flip, right? Number of heads. And so the probability of heads, if I flipped my coin 15 times and I observed what I have written down here, I see that this is going to look like heads, heads, tails, 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 heads, tails, tails, heads, tails, heads, tails. And I observed 5 heads, right? The frequency of heads out of the 15 times that I saw it, or 1/3, right? That would be the common fraction. And common fractions, by the way, are one of the most popular ways of writing probabilities. So we prefer common fractions because they're exact, right? There's no round off. Or if we were going to write this as a decimal, then I would be writing this as approximately, and this would look like approximately 0.333. Now, a lot of textbooks will say that when they want this rounded off, they'll call it 3 significant digits or 3 significant figures or something like that. And what they want on this is really as if it's in scientific notation. So I'm going to write this as if in scientific. And the reason for that is because they want to get 3 digits that they could compare in case the probability was really, really teeny tiny. So if I were going to write this in scientific notation, it would look like 3.33 times 10 to the negative 1 power, right? And this is what most books are looking for when they say that 3 digits, that they want that right there. Not that they necessarily want the 3 decimals, because if I have a number like 0.0000333, you see, I would get 0. And then if I were going to compare that to 0.0000333 here, then I have no difference, right? At 3 decimals here or here, there's no difference between these. But you see, there is actually a difference because this has 2 more zeros before it gets to the 3's. And so this probability is actually slightly higher than this probability. Hence the reason that we use the 3 decimals here, because here you would see that this is 3.33 times 10 to the negative, and this one would be, let's see, 1, 2, 3, 4, 5, 6, and this one here would be 3.33 times 10 to the negative 5. And because of that, you would see, oh yeah, this one is a bigger probability than that one, and you would have a comparison. Now, what this is talking about is how you can do this in Excel. So basically what I did was I coded in order to get these. I didn't actually flip my coin. Now our TI calculators also are able to do random digits as well and random numbers. And the PRB menus, we can actually do those random number generation. The versions of Excel vary kind of greatly in how you can do this random number generation, and so I typically don't go over this in class just because it really does depend upon the version of Excel. Depends upon if it's a PC or if it's a Mac. I found my Mac a little bit more difficult to do the random number generation than I did with my PC, and therefore it's just not worth the extra time to go over. All right, the classic approach based upon equally likely outcomes is another approach to probability. And this, like I was saying before, this classic approach is like our theoretical. Okay, so this is based upon equally likely outcomes, and that is important. Okay, you can't have one more probable to occur than another, but this again is going to look like your population. So this one, the probability of event A is occurring, we symbolize it with S over N, which kind of sounds familiar, right? F over N, S over N. Very similar. And N is the number of simple events. And so we're coming back to that idea of building our sample space, right? So the number of simple events, and this is the number of ways that our event can occur. And this would come back to looking at the simple event and then defining our simple events in the universe, and then defining our event and saying, okay, how many of them are actually going to satisfy this particular instance. So if we're looking at the probability of getting ahead when we flip 2 coins, or when we flip a coin, right? So H is the number of heads. if we take a look at flipping a coin, well, we get two possible outcomes, right? Two simple events, a heads or a tail, and one of those is equal to a head. So our probability here, looking at this, would be 0.5, and we really should have 0, 0 out here, although we usually don't write it that way. That's how it should be written. That would be the instance. Now remember when we were looking at the probability of two heads in 3 flips? Well, where we would start is we would start back there at, okay, well, how many possible outcomes are there? Well, there were 8 possible outcomes, weren't there? And we found that 3 of those 8 were our simple events. So we have 3.75 as our probability there of getting our two heads in 3 flips of a coin. And again, that's because there are 8 events that are likely, and those are our simple events, and then 3 of those are the ones that would give us the outcomes of 2 heads in 3 flips. Remember again, exactly. Now I have another example here, and this one's taken from drawing cards from a deck of 52. So I have a deck of 52 cards, and in that I want to know what the probability of drawing a king is. Well, if I want the probability of drawing a king, I can start out by saying, okay, what are the simple events? Well, the simple events are the 52 cards that are present. And then how many ways can I see a king? Well, there are 4 kings in the deck of cards, and so that would be 4 out of 52. And then, of course, this reduces to 1/13. And then if I were going to go for a decimal, which 1/13 is, not, although not a common fraction, still is very much preferred. So 1 divided by 13, which is going to give us a repeating non-terminating decimal, that will give me 0.0769 approximately, 0.0769. Now you notice here that I have gone out, so I get 3 digits here, not counting this as one of my 3, this being my 3. So I approximately 0.0769 as my probability as a rounded decimal. And again, 1/13 is much more exact. Now, it is interesting to notice here that when you look at 4/52 and 1/13, that these actually can be different ways of defining the simple events, because I can define the simple events truly as the most simplistic way of looking at it as 52 cards in the deck, but I could also define the simple events as the cards that are possible that I draw from the deck, right? I have 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, 10s, jacks, queens, kings, and aces. Those are 13 different possibilities, and only one of those possibilities are of the 13. So that's yet another way of looking at it. So those are the classic approach of finding probability, which differs from the relative frequency approach. So the just to kind of compare and contrast here, let's compare and contrast this one. This is the probability of getting ahead that we got by the classic approach, 0.5, right? And then this is the probability with the relative frequency that we got for getting ahead. And those two are talking about the exact same thing, but one is a sample and one is a population. So this one here with a relative frequency is a sample, and we notice that that does not quite equal what we get from our theoretical, from our population. So the sample is meant to mimic that population, but it doesn't always mimic it exactly, which is exactly what we learned in Chapter 1, that you don't always get your sample to tell you exactly what the population is. There's sampling error going to always exist. So that is what we're going to talk about a little bit next in the law of large numbers. So I'll come back and we'll talk about that in our next video, the law of large numbers.